Right now, somewhere above your head, an object the size of a small mountain is hurtling through space at 130,000 miles per hour, fast enough to cross the continental United States in under 3 minutes, fast enough to outrun any human-made spacecraft by orders of magnitude. This ancient wanderer has been traveling through the cosmic void for potentially billions of years, carrying chemical signatures from stellar environments we've never encountered, shaped by gravitational forces from stars that died before our sun was born. 3I Atlas sounds like just another astronomical catalog number, until you realize what it represents. Our third confirmed visitor from interstellar space, and by far our most mysterious. Unlike the comets and asteroids born in our solar system's familiar gravitational embrace, this object emerged from the space between stars where the normal rules of orbital prediction become exercises in educated guessing, rather than precise calculation. The mathematics tell us it will pass safely by Earth at a comfortable distance, but mathematics assume perfect knowledge of an imperfect universe. When you're dealing with something that has wandered the galaxy since before complex life existed on our planet, something whose internal structure remains hidden beneath layers of ancient ice and rock, something that defies every model we've constructed about how objects behave in the presence of our sun, the comfortable boundaries between scientific certainty and cosmic anxiety begin to dissolve. Tonight, we venture into that uncertain territory where ancient messengers from distant stars force us to confront uncomfortable questions about the limits of human knowledge and the terrifying possibility that some cosmic threats remain undetectable until the moment they reshape our world forever. Where you're listening from tonight, and what time it is in your corner of the world, there's something remarkable about how astronomy connects us all under the same cosmic canopy, regardless of our earthly coordinates. Let's dive into what 3I Atlas might mean for our world and our future among the stars. The first hint that something extraordinary was racing toward our solar system came not from a dramatic telescope revelation, but from the methodical clicking of automated survey cameras scanning the southern sky. On January 15, 2024, the Asteroid Terrestrial Impact to Last Alert System telescope in Chile captured what appeared to be just another faint smudge of light moving against the star field. Within hours, follow-up observations confirmed what the initial measurements suggested, but seemed almost impossible to believe. This wasn't another piece of solar system debris following a predictable, elliptical orbit around our sun. The mathematics were unambiguous. This object was moving on a hyperbolic trajectory, unbound by solar gravity, originating from the depths of interstellar space. The discovery triggered protocols developed over decades of near-Earth object surveillance. Within 24 hours, observatories across 3 continents had swung their instruments toward the coordinates provided by the Minor Planet Center. The European Southern Observatory's Very Large Telescope in Chile's Atacama Desert captured the first detailed images, revealing a fuzzy star-like point surrounded by the telltale coma that marks active cometary behavior. But even these early observations hinted at something unusual. The brightness variations didn't match the patterns astronomers expected from typical comets, and the spectral signatures emerging from preliminary analysis suggested chemical compositions that challenged established models of how icy bodies form around other stars. The Hubble Space Telescope received priority scheduling within a week of discovery, interrupting previously planned observations to focus on this interstellar interloper. The images that emerged showed classic cometary features, a bright nucleus surrounded by an expanding envelope of gas and dust. But the scale and intensity of the activity surprised researchers. Most comets remain relatively inactive at 3I Atlas's current distance from the Sun. Yet this ancient wanderer was already producing a detectable coma extending hundreds of thousands of kilometers from its nucleus. The international response demonstrated modern astronomy's remarkable coordination capabilities. Radio telescopes from Arecibo to Parkes began monitoring the object for any artificial signals, while infrared observatories attempted to measure its thermal properties and internal structure. Ground-based photometry networks tracked its brightness changes, searching for rotation periods and signs of structural instability. The James Webb Space Telescope allocated precious observation time to capture detailed spectra of the coma's chemical composition, revealing molecular fingerprints that would prove crucial for understanding this visitor's alien origins. Yet, with each new observation, 3I Atlas became more mysterious rather than less. Its size estimates ranged wildly depending on assumptions about surface reflectivity and internal density. Its chemical signatures didn't match any known population of comets from our solar system, suggesting formation conditions around very different types of stars. Most troubling of all, its exact trajectory remained uncertain despite weeks of precise astrometric measurements, with small but persistent discrepancies that hinted at non-gravitational forces acting on the object in ways that current models couldn't fully predict. The growing realization among the astronomical community was both thrilling and unsettling. 3I Atlas represented far more than just another interstellar visitor. It was an ancient messenger carrying information about stellar environments we'd never encountered, chemical processes that occurred billions of years ago, and physical behaviors that stretched the boundaries of established cometary science. But it was also an object whose ultimate intentions, if such a term could apply to natural phenomena, remained fundamentally unknowable, despite the most sophisticated observational campaign ever mounted against an interstellar intruder. The orbital mechanics of 3I Atlas present a puzzle wrapped in mathematical uncertainties that grow more troubling with each refined calculation. Unlike the predictable elliptical paths traced by objects born within our solar system's gravitational embrace, this interstellar wanderer follows a hyperbolic trajectory that carries it on a one-way journey through our cosmic neighborhood. Its orbital eccentricity of approximately 1.7 places it firmly in the category of unbound visitors, objects moving too fast for solar capture, destined to pass through and continue into the interstellar void. But the devil lurks in the details that resist precise measurement. 3I Atlas approaches our solar system at a velocity of roughly 32 kilometers per second relative to the Sun, a speed that dwarfs the orbital velocities of native solar system objects. This extreme velocity creates its own problems for trajectory prediction. Small measurement errors in position or velocity, insignificant for slower-moving asteroids, become magnified over the months of 3I Atlas's passage, creating uncertainty cones that expand like the beam of a flashlight the farther we project into the future. The object's unusual approach angle compounds these difficulties. Most interstellar visitors should arrive from directions that reflect the local stellar neighborhood's motion relative to our solar system. 3I Atlas, however, approaches from a trajectory that suggests either a more distant origin or a complex history of gravitational encounters that have scrambled its original motion vector. This unusual geometry makes it challenging to backtrack the object's previous path or predict how it might respond to gravitational perturbations during its solar system passage. Non-gravitational forces add another layer of uncertainty to an already complex prediction problem. As 3I Atlas heats up in response to increasing solar radiation, sublimating ices create jets of gas and dust that act like tiny rocket engines, pushing the object in directions that depend on the location and orientation of active vents on its surface. For typical comets, these outgassing forces follow somewhat predictable patterns based on solar heating models. But 3I Atlas exhibits unusual chemical signatures that suggest its outgassing behavior may not conform to established patterns. The Yarkovsky effect, named after the Russian engineer who first described it, represents another source of trajectory uncertainty. As 3I Atlas rotates, it absorbs solar energy during its day and re-radiates that energy as heat during its night. This creates a slight but persistent force that can alter the object's orbit over time. The magnitude of this effect depends critically on the object's size, rotation period, thermal properties, and surface characteristics, all of which remain poorly constrained despite intensive observational campaigns. Perhaps most unsettling are the cascade effects that could amplify small perturbations into major trajectory changes. 3I Atlas will pass relatively close to Jupiter during its outbound journey, potentially experiencing gravitational influences that could alter its path in subtle but significant ways. Computer simulations suggest that variations in the object's mass, density, or outgassing behavior could lead to different gravitational outcomes, creating a branching tree of possible future trajectories that includes, in low-probability scenarios, Earth-crossing orbits. The fundamental challenge lies in the accumulation of uncertainties over cosmic timescales. 3I Atlas has been wandering interstellar space for potentially billions of years, during which it may have experienced countless gravitational encounters with stars, planets, and other massive objects. Each encounter would have modified its trajectory in ways that are impossible to reconstruct from current observations. The object we observe today represents the endpoint of a chaotic dynamical history but has erased most traces of its original motion. This trajectory paradox extends beyond mere academic uncertainty to touch on fundamental questions about predictability in celestial mechanics. Our ability to forecast the motions of planets and asteroids with extraordinary precision depends on having complete initial conditions and understanding all relevant forces. The 3I Atlas challenges both assumptions, presenting us with an object whose history is largely unknown and whose future behavior depends on physical processes we can measure only imperfectly. The sobering reality is that despite deploying our most sophisticated observational and computational tools, we cannot definitively rule out trajectory changes that could transform 3I Atlas from a harmless visitor into an existential threat. The mathematics that govern orbital mechanics remain as precise as ever, but they operate on inputs that carry irreducible uncertainties about an object that embodies billions of years of cosmic chaos we can never fully reconstruct or predict. When the James Webb Space Telescope turned its infrared gaze toward 3I Atlas in early February 2024, the spectroscopic data that streamed back to Earth revealed a chemical portrait unlike anything in our catalogue of known comets. The molecular signatures dancing through the object's expanding coma told a story of formation conditions so alien to our solar system's history that they forced astronomers to confront fundamental gaps in our understanding of how icy bodies develop around other stars. The most striking anomaly emerged in the water-to-carbon monoxide ratio, a diagnostic tool that typically reveals the temperature conditions under which comets originally formed. Solar system comets display predictable ratios that reflect the temperature gradients in our primordial nebula disk, with water ice dominating in the cooler outer regions and more volatile species like carbon monoxide concentrated in the coldest zones. 3I Atlas shattered these expectations entirely, showing carbon monoxide abundances nearly 10 times higher than any previously observed comet, suggesting formation in environments far colder than anything our solar system experienced during its birth. Even more puzzling was the near absence of traditional comet constituents that should accompany such high carbon monoxide concentrations. Nitrogen compounds, which typically appear alongside carbon monoxide in the coldest regions of planetary formation disks, were barely detectable in 3I Atlas's spectrum. Methane, another expected companion of extreme cold formation, appeared in ratios that defied theoretical predictions. The chemical fingerprint resembled no known population of solar system objects, terrestrial or otherwise. The organic chemistry revealed by deeper spectroscopic analysis painted an equally mysterious picture. Complex carbon-based molecules, typically associated with interstellar dust processing, appeared in unexpected abundances, suggesting that 3I Atlas had undergone chemical evolution during its billion-year journey through space. Cosmic ray bombardment and exposure to the harsh interstellar radiation field had apparently modified its surface composition in ways that no solar system comet has ever experienced, creating a hybrid chemistry that blends primordial formation signatures with the accumulated effects of interstellar weathering. Perhaps most troubling were the isotope ratios embedded within these molecular signatures. The relative abundances of different forms of carbon, nitrogen, and oxygen atoms carry information about the nuclear processes operating within the star around which 3I Atlas originally formed. The measurements suggested formation around a stellar environment with significantly different nuclear chemistry than our Sun, possibly a more massive star with a different fusion history, or perhaps a stellar system enriched by previous generations of supernovae in ways our local galactic neighborhood never experienced. The temporal implications of these chemical signatures stretch the imagination. If 3I Atlas indeed formed around a different type of star, its chemistry preserves a snapshot of galactic conditions that may have existed billions of years ago, when stellar populations, interstellar medium compositions, and planetary formation processes differed substantially from current conditions. The object serves as a chemical fossil, carrying molecular evidence of cosmic environments that no longer exist in their original forms. These compositional mysteries complicate every attempt to predict 3I Atlas's future behavior as it approaches the Sun. Typical comet models rely on understanding how different ices sublimate under solar heating, creating the gas and dust that forms cometary and tails. But models calibrated on solar system objects may not apply to chemistry forged under alien stellar conditions. The unusual molecular inventory could lead to unpredictable outgassing patterns, unexpected structural instabilities, or gas production rates that differ dramatically from theoretical expectations. The density and porosity inferred from these chemical measurements add another layer of uncertainty. The unusual volatile ratios suggest either formation in a very low-density environment, where molecules could condense in ratios impossible under higher pressure conditions, or subsequent processing that has altered the original chemical architecture. Either interpretation implies internal structures that may not behave predictably under the thermal and gravitational stresses of solar system passage. Most unsettling is what these chemical anomalies reveal about our fundamental ignorance of interstellar object populations. 3I Atlas represents our most detailed chemical analysis of material that formed around another star, and it conforms to none of our theoretical expectations. If this level of chemical diversity exists among interstellar wanderers, our models for predicting their behavior, assessing their threat potential, and understanding their origins may be fundamentally inadequate for dealing with objects that carry billions of years of alien stellar chemistry through our cosmic neighborhood. The fundamental problem haunting every assessment of 3I Atlas's threat potential lies in a deceptively simple question that resists definitive answer. Exactly how big is this ancient wanderer? Size determines everything in impact scenarios, from the energy release during atmospheric entry to the scale of global devastation that might follow. Yet despite months of intensive observation using humanity's most sophisticated telescopes, the object's true dimensions remain shrouded in uncertainty that translates directly into vastly different risk calculations. Current size estimates span a range that encompasses dramatically different impact scenarios. Conservative measurements based on reflected sunlight and thermal emission suggest a nucleus perhaps 2 to 3 kilometers in diameter, roughly the size of a small mountain. More liberal interpretations of the observational data allow for objects up to 8 kilometers across, approaching the scale of the asteroid that ended the age of dinosaurs 66 million years ago. This factor of 3 uncertainty, in linear dimensions, corresponds to a 27-fold difference in mass and kinetic energy, transforming 3I Atlas from a regional catastrophe into a potential civilization-ending event. The challenge stems from the fundamental difficulty of measuring objects surrounded by active cometary comet. As 3I Atlas approaches the Sun, solar heating sublimates surface ices, creating an expanding envelope of gas and dust that obscures direct observation of the underlying nucleus. Astronomers must disentangle the light reflected from the solid nucleus from the scattered radiation produced by millions of dust particles in the surrounding coma, a process complicated by unknown dust production rates, particle size distributions, and scattering properties that depend on the object's alien chemical composition. Traditional techniques for estimating comet nucleus sizes rely on thermal infrared observations that measure heat radiated from the object's surface, but these measurements require assumptions about surface properties, thermal conductivity, and heat retention that may not apply to objects with 3I Atlas's unusual chemical signature. The exotic volatile ratios detected in its coma suggest surface compositions unlike any solar system comet, potentially altering thermal properties in ways that could lead to systematic errors in size estimates. Even more troubling is the possibility that 3I Atlas might not be a single solid object at all, but rather a loose aggregation of smaller components held together by weak gravitational and cohesive forces. Such rubble pile structures, common among asteroids and some comets, behave very differently under stress than monolithic objects. A loosely bound aggregate might survive the billion-year journey through interstellar space, only to disintegrate when subjected to tidal forces, thermal stress or rotational instabilities during its passage through our solar system. The structural uncertainty carries profound implications for impact risk assessment. A solid 3-kilometer object would likely survive atmospheric entry largely intact, creating a single massive crater and localized devastation. The same mass distributed among dozens of smaller rubble pile components might fragment in the atmosphere, spreading destruction across a much wider area, but potentially reducing the peak energy deposition at any single location. Alternatively, structural failure during solar heating could scatter debris across multiple Earth-crossing trajectories, transforming a single impact threat into a sustained bombardment lasting months or years. Rotation period measurements add another dimension to the structural puzzle. 3I Atlas appears to tumble chaotically rather than rotating about a stable axis, suggesting either an highly irregular shape or internal mass distribution, or possibly indicating ongoing structural changes as thermal cycling and outgassing stress the object's cohesive strength. Chaotic rotation often signals impending fragmentation in comets, but the timescales for such processes remain unpredictable, particularly for objects with unknown internal architectures. The observational limitations that constrain size estimates also apply to density measurements. Another crucial parameter for impact modeling, low-density objects rich in ice and volatile materials might disrupt completely in Earth's atmosphere, creating spectacular but relatively harmless airbursts similar to the Chelyabinsk event of 2013. High-density objects dominated by rock and metal would penetrate deeper into the atmosphere, potentially reaching the surface with devastating consequences, without knowing 3I-TECLES's internal composition and structure. Impact modelers cannot definitively predict whether atmospheric entry would result in airburst, surface impact, or some combination of both effects. These structural uncertainties underscore a deeper problem with assessing threats from interstellar objects. Our models for predicting asteroid and comet behavior rely on statistical knowledge accumulated from studying thousands of solar system objects with similar formation histories and evolutionary pathways. 3I Atlas represents a sample size of one from an entirely different population, shaped by stellar environments and evolutionary processes we've never directly observed. The assumptions underlying our hazard assessment models may simply not apply to objects carrying billions of years of alien stellar system chemistry and physics. The stark reality is that despite deploying our most advanced observational capabilities, we cannot determine with confidence whether 3I Atlas represents a mountain-sized harbinger of regional destruction or a city killer capable of global catastrophe. This fundamental uncertainty about such a basic physical property illustrates the profound challenges of assessing threats from visitors, whose origins, structures, and behaviors remain largely mysterious despite intensive study. As 3I Atlas accelerates toward its closest approach to the Sun, scheduled for late September 2024, solar heating will trigger a process that transforms this ancient ice ball into something far more dynamic and potentially dangerous. The outgassing phenomenon that creates the spectacular tails of visible comets also generates vast clouds of debris that could pose significant risks to both human spacecraft and, under certain circumstances, Earth itself. Understanding this process becomes crucial for assessing whether 3I Atlas will pass quietly through our solar system or leave behind a trail of hazardous material that could threaten our planet for years to come. The physics of cometary outgassing operates like a slow-motion explosion spanning months rather than milliseconds. As solar radiation penetrates the object's surface, subsurface ices transition directly from solid to gas without passing through a liquid phase, creating internal pressure that eventually finds release through surface vents and fissures. For typical solar system comets, this process follows predictable patterns based on well-understood relationships between solar distance, surface temperature, and ice sublimation rates. 3I Atlas, with its alien chemistry and unknown internal structure, may not conform to these established models. The unusual volatile inventory detected in 3I Atlas's early outgassing activity suggests gas production rates that could exceed typical cometary behavior by substantial margins. The high carbon monoxide concentrations observed spectroscopically indicate ices that sublime at much greater distances from the Sun than water ice, potentially creating sustained outgassing activity throughout the object's passage through the inner solar system. This extended activity period increases both the total amount of material ejected and the spatial volume over which debris could be distributed. Historical precedents from solar system comets provide sobering examples of how outgassing can create hazardous debris fields. Comet Shoemaker-Levy 9 demonstrated the extreme case when tidal forces fragmented the object into multiple pieces that subsequently impacted Jupiter in 1994. More recently, Comet Ison disintegrated completely during its 2013 solar passage, creating a debris stream that persisted for months. Even intact comets like Halley and Swift-Tuttle have generated meteor streams that Earth encounters annually, producing visible shooting stars when dust particles burn up in our atmosphere. The scale of debris production from 3I Atlas remains highly uncertain due to its unknown internal structure and unusual composition. If the object consists of a loosely consolidated rubble pile held together by weak cohesive forces, thermal stress from solar heating could trigger catastrophic disintegration, releasing millions of tons of rocky and icy fragments into interplanetary space. Alternatively, a more structurally robust object might maintain its integrity while still producing substantial amounts of dust and gas through surface sublimation. The spatial distribution of ejected material depends critically on the location and orientation of active vents on 3I Atlas's surface. parameters that remain poorly constrained despite intensive observational campaigns. Asymmetric outgassing can create jet-like plumes that preferentially eject material in specific directions, potentially concentrating debris along particular orbital trajectories. If these trajectories intersect Earth's orbital path, our planet could encounter dense concentrations of cometary debris months or years after the parent object has passed. Particle size distributions within the debris field present another unknown factor with significant implications for impact hazard assessment. Microscopic dust particles pose minimal direct threat to Earth, but could affect satellite operations and create spectacular meteor displays. Larger fragments ranging from pebbles to boulders could survive atmospheric entry, potentially causing ground damage over wide areas. The size distribution depends on the specific mechanisms driving fragmentation, which may operate differently for objects with 3A Atlas's exotic composition. The temporal evolution of debris fields adds complexity to hazard assessment calculations. Initial ejection velocities are typically low, measured in meters per second rather than kilometers per second, but gravitational perturbations and solar radiation pressure can modify debris trajectories over time. Material ejected early in 3I Atlas's approach could follow very different orbital paths than debris released near perihelion, creating multiple streams of hazardous material spread across different regions of the solar system. Tracking capabilities for small debris remain severely limited despite advances in space surveillance technology. Current detection systems can reliably track objects larger than about 10 centimeters in Earth orbit, but this threshold increases dramatically for objects in heliocentric trajectories. Debris from 3I Atlas could include dangerous fragments too small for detection, but large enough to cause significant damage upon atmospheric entry. The electromagnetic environment created by outgassing presents additional complications for both observation and hazard mitigation. Dense clouds of ionized gas can interfere with radar tracking and radio communications, potentially degrading our ability to monitor the debris field's evolution or coordinate response efforts. The plasma environment might also affect the trajectories of charged dust particles in ways that are difficult to predict without detailed knowledge of the local magnetic field configuration. Perhaps most concerning is the possibility that 3I Atlas could establish a semi-permanent debris stream along its orbital path, similar to the annual meteor showers associated with periodic comets. Unlike those predictable displays, a debris stream from an interstellar visitor would follow a hyperbolic trajectory that could intersect Earth's orbit at unpredictable intervals, creating an ongoing impact hazard that persists long after the parent object has departed our solar system. The fundamental challenge lies in predicting debris field characteristics for an object whose behavior may not conform to any established models of cometary activity, leaving us to prepare for hazards we cannot fully anticipate or quantify. The gravitational architecture of our solar system operates like an intricate clockwork mechanism, with each massive body influencing the motion of every other object through invisible forces that stretch across billions of kilometers. For 3I Atlas, racing through this gravitational maze at unprecedented velocity, even minor encounters with our solar system's giants could trigger cascade effects that transform a predictable flyby into an unpredictable threat. The challenge lies in understanding how the accumulated gravitational influences of multiple planets could conspire to alter this ancient wanderer's trajectory in ways that current models struggle to anticipate. Jupiter dominates the gravitational landscape beyond Mars, wielding an influence that extends far beyond its visible disk. With a mass more than twice that of all other planets combined, Jupiter acts as the solar system's gravitational shepherd, capable of dramatically altering the orbits of passing objects. 3N Atlas will approach within roughly 4 astronomical units of Jupiter during its outbound journey, close enough to experience significant gravitational deflection. Computer simulations suggest this encounter could alter the object's velocity by several kilometers per second, potentially redirecting it onto a fundamentally different trajectory. The three-body problem that governs interactions between 3-eyed Atlas, Jupiter, and the Sun represents one of classical mechanics' most notorious challenges. Unlike the elegant mathematical solutions available for two-body systems, three-body interactions exhibit chaotic behavior that makes long-term predictions extraordinarily sensitive to initial conditions. Small uncertainties in 3-eyed Atlas's current position and velocity, well within observational error margins, could lead to dramatically different outcomes during the Jovian encounter. Saturn's influence adds another layer of complexity to trajectory predictions. Although more distant and less massive than Jupiter, Saturn's gravitational field could provide the additional perturbation needed to push 3i Atlas from a hyperbolic escape trajectory onto an elliptical orbit that brings it back into the inner solar system. The timing of these planetary encounters becomes crucial, with gravitational assists occurring when the object passes closest to each planet's orbital path. The cumulative effect of multiple planetary perturbations creates what dynamicists call resonance chains, where successive gravitational encounters amplify rather than cancel each other's effects. If 3i Atlas experiences a particular sequence of planetary flybys, the combined gravitational influences could deflect the object by much larger amounts than any single encounter would suggest. These resonance effects are notoriously difficult to predict because they depend on precise timing relationships between the object's motion and planetary positions. Tidal forces present an additional mechanism through which planetary encounters could affect 3i Atlas's trajectory. As the object passes close to massive planets, differential gravitational forces across its structure could induce internal stresses that trigger fragmentation or alter its rotation state. Changes in rotation could modify how outgassing forces affect the object's motion, creating feedback loops between gravitational perturbations and non-gravitational accelerations that further complicate trajectory predictions. The asteroid belt represents another source of potential gravitational perturbations during 3i Atlas's passage through the inner solar system. While individual asteroids are too small to significantly deflect such a massive object, the cumulative gravitational influence of thousands of asteroids could produce measurable trajectory changes over time. These collective effects are extremely difficult to model accurately because they require detailed knowledge of asteroid positions and masses that remains incomplete despite decades of observation. Relativistic effects, though small, become non-negligible for objects moving at 3i Atlas's extreme velocity. General relativity predicts that massive bodies like the Sun curve spacetime in ways that affect the motion of passing objects beyond what Newtonian gravity alone would suggest. For most solar system objects, these relativistic corrections are tiny, but 3i Atlas's high speed amplifies these effects to potentially observable levels that could influence long-term trajectory predictions. The fundamental unpredictability emerges from the exponential growth of uncertainties in chaotic dynamical systems. Mathematical analysis shows that trajectories in the outer solar system can diverge exponentially from initially similar conditions, meaning that measurement uncertainties double approximately every orbital period. For 3i Atlas, this sensitivity to initial conditions means that current observational precision may be insufficient to predict its exact trajectory beyond the next several planetary encounters. Perhaps most troubling is the possibility of trajectory bifurcation, where small changes in current conditions lead to qualitatively different future outcomes. Computer models suggest that variations in 3i Atlas's mass or internal structure within current observational uncertainties could determine whether it follows a hyperbolic escape trajectory or becomes gravitationally captured into a highly elliptical orbit. The difference between these outcomes could determine whether the object departs our solar system forever or returns as a periodic visitor with potentially Earth-crossing potential. The unbody problem governing interactions between 3i Atlas and all solar system planets simultaneously represents a computational challenge that pushes current modeling capabilities to their limits. Even the most sophisticated numerical integrations must make approximations about planetary masses, positions, and the object's own properties that could accumulate into significant errors over the months of its solar system passage. This gravitational uncertainty principle means that despite our most advanced computational tools and observational capabilities, we cannot definitively predict whether 3i Atlas will depart our solar system as expected or undergo trajectory modifications that could transform it from a harmless visitor into a persistent threat requiring ongoing monitoring and potential mitigation efforts. The nightmare scenario that haunts every cometary physicist studying 3i Atlas isn't a single catastrophic impact, but rather the possibility that this ancient wanderer could disintegrate during its solar passage, creating a devastating shotgun blast of fragments scattered across multiple Earth-crossing trajectories. Fragmentation transforms a manageable single-object threat into a chaotic swarm of unpredictable projectiles that could overwhelm our detection capabilities and render traditional deflection strategies completely useless. The physics governing cometary breakup operates through multiple mechanisms that could affect 3i Atlas as it experiences the intense thermal and gravitational stresses of inner solar system passage. Thermal fragmentation occurs when differential heating creates internal pressure gradients that exceed the object's structural strength, As solar radiation penetrates the surface, subsurface ices sublime rapidly, creating gas pockets that can literally blow the object apart from within. The process resembles a pressure cooker explosion occurring in slow motion across weeks or months. Tidal disruption presents another fragmentation pathway that becomes increasingly likely as 3I Atlas approaches its September perihelion. The Sun's gravitational field creates differential forces across the object's structure, with the near side experiencing stronger attraction than the far side. For objects with low internal cohesion, these tidal forces can overcome the weak gravitational self-attraction holding the fragments together, pulling the object apart, like taffy stretched beyond its breaking point. Rotational instability adds a third mechanism that could trigger catastrophic breakup. Many comets spin up as outgassing creates asymmetric thrust forces, similar to how a garden sprinkler rotates under water pressure. If 3I Atlas's rotation rate exceeds its structural limits, centrifugal forces could overcome internal cohesion, causing the object to fly apart like a spinning flywheel that exceeds its design specifications. The chaotic tumbling already observed in 3I Atlas suggests internal mass asymmetries that could amplify rotational stresses. Historical precedents demonstrate how spectacular and dangerous cometary fragmentation can become. Comet Shoemaker, Levy 9, fragmented into more than 20 distinct pieces during a close encounter with Jupiter in 1992, creating a string of impacts that pounded the giant planet. 2 years later, with the combined energy of millions of nuclear weapons, Comet Ison completely disintegrated during its 2013 solar passage, transforming from a single object into a diffuse cloud of debris that dispersed across the inner solar system. More recently, Comet Lended exhibited signs of structural instability during its 2021 passage, developing multiple disconnection events where portions of its tail separated from the nucleus, suggesting ongoing fragmentation processes. Even relatively stable comets, like Halley, shed substantial amounts of material during each solar encounter, gradually diminishing their size through a process of slow-motion disintegration spanning millennia. The fragmentation of 3I Atlas would create a debris field unlike anything in recorded astronomical history. Unlike periodic comets that fragment along predictable orbital paths, an interstellar object's hyperbolic trajectory means that fragments would scatter across a much wider range of solar system space. Computer simulations suggest that breakup near perihelion could distribute fragments across orbital paths ranging from Venus crossing to asteroid belt crossing trajectories, with some pieces potentially redirected onto Earth intersecting orbits. The size distribution of fragments poses another critical uncertainty. Laboratory studies of ice and rock samples suggest that cometary fragmentation typically follows power law distributions, producing many small pieces and fewer large ones, but the exact scaling relationships depend on internal structure, composition, and the specific stresses triggering breakup. 3A Atlas's unusual chemistry and unknown internal architecture make it impossible to predict whether fragmentation would produce predominantly dust-sized particles or retain substantial mountain-sized chunks capable of surviving atmospheric entry. Fragment velocities add another dimension to the threat assessment problem. Initial separation velocities during breakup are typically measured in tens of meters per second, but gravitational perturbations and differential solar radiation pressure can modify these trajectories over time. Fragments with slightly different surface properties or rotation states could evolve onto dramatically different orbital paths, spreading the threat across multiple years and orbital geometries. The observational challenges of tracking multiple fragments would strain current space surveillance capabilities beyond their breaking point. Detecting and cataloging hundreds or thousands of debris pieces, each following its own trajectory through three-dimensional space, represents a computational and logistical nightmare that could overwhelm ground-based tracking networks. Many fragments might remain undetected until they approach Earth, providing little or no advance warning of potential impacts. The temporal distribution of fragment arrivals could extend the threat over years or decades, unlike a build impact event that concentrates all destructive energy in one location and time. A fragmented 3I Atlas could subject Earth to sustained bombardment as different pieces arrive along their various orbital paths. This scenario would require maintaining planetary defense readiness for extended periods while dealing with multiple simultaneous threats. Perhaps most disturbing is the possibility of cascade fragmentation, where initial breakup creates fragments that subsequently break apart themselves under continued thermal and gravitational stress. This process could transform 3I Atlas from a single object into an ever-expanding cloud of debris, that continues to evolve and threaten Earth encounters for years after the original fragmentation event. The fundamental challenge lies in predicting fragmentation behavior for an object whose internal structure, cohesive strength, and material properties remain largely unknown despite intensive study. Current models, calibrated on solar system comets, may not apply to objects with 3I Atlas's exotic composition and billion-year history of interstellar weathering, leaving us unprepared for fragmentation scenarios that could unfold in ways we cannot anticipate or effectively counter. The atmospheric consequences of a major impact from 3I Atlas or its fragments would unleash a cascade of environmental catastrophes that could fundamentally alter Earth's climate system for years or decades. Understanding these potential effects requires examining how objects of different sizes interact with our planet's atmosphere, and the terrifying efficiency with which kinetic energy converts into widespread atmospheric disruption capable of triggering global climate shifts. When a large object strikes Earth's atmosphere at cosmic velocities, the initial interaction creates a shock wave that compresses and superheats atmospheric gases to temperatures exceeding those found in stellar interiors. A 3-kilometer fragment from 3I Atlas, traveling at roughly 30 kilometers per second, would release kinetic energy equivalent to several 100 million megatons of TNT, dwarfing the entire global nuclear arsenal. This energy release occurs within seconds, creating a fireball that expands rapidly through the atmosphere and injects enormous quantities of vaporized rock, ice, and atmospheric gases into the upper atmosphere. The immediate atmospheric heating from such an impact would create thermal radiation intense enough to ignite vegetation across vast areas of the planet's surface. Computer models suggest that fragments larger than 2 kilometers in diameter could generate thermal pulses capable of starting wildfires across entire continents, pumping billions of tons of smoke and soot into the atmosphere. These combustion products would join impact-generated dust to create a global atmospheric shroud that blocks sunlight from reaching Earth's surface. The composition of 3I Atlas adds another dimension to atmospheric disruption scenarios. Unlike rocky asteroids, this object contains substantial amounts of water, ice, and volatile compounds that would vaporize completely during atmospheric entry. The injection of vast quantities of water vapor into the upper atmosphere could trigger complex chemical reactions that deplete ozone concentrations, reducing the planet's natural protection against harmful ultraviolet radiation. Simultaneously, the unusual carbon chemistry detected in 3I Atlas's spectrum could introduce atmospheric pollutants with unknown environmental effects. Global dust loading represents perhaps the most dangerous long-term consequence of major impact. Fine particles ejected by the impact explosion can remain suspended in the atmosphere for months or years, gradually settling out while blocking solar radiation from reaching the surface. The amount of dust injection depends critically on impact location, with strikes in continental crust producing far more atmospheric debris than oceanic impacts. A land-based impact from a large 3I Atlas fragment could inject enough dust to reduce global temperatures by several degrees Celsius. The precedent set by the Chicxulub impact 66 million years ago demonstrates how atmospheric disruption can cascade into mass extinction events. That impact from an object roughly 10 kilometers in diameter created global atmospheric conditions so hostile that it eliminated roughly 75% of all species on Earth. While 3I Atlas appears smaller than the Chicxulub impactor, even a fragment half that size could trigger climatic effects severe enough to disrupt global agriculture and threaten modern civilization. Nuclear winter scenarios provide another framework for understanding potential atmospheric consequences. The dust and smoke injected by a major impact would reduce surface temperatures through mechanisms similar to those predicted for large-scale nuclear war. Agricultural regions could experience growing season failures for multiple consecutive years as reduced sunlight and lower temperatures prevent crops from reaching maturity. The global food supply system, already stressed by climate change and population growth, might collapse completely under such conditions. Ocean impacts present their own atmospheric hazards through massive steam injection and tsunami generation. If 3I Atlas or a large fragment struck the ocean, the impact would vaporize enormous volumes of seawater, creating water vapor plumes that could alter global precipitation patterns for years. The resulting atmospheric moisture could trigger unprecedented storms and flooding in some regions while creating severe droughts in others. Coastal populations worldwide would face immediate tsunami threats followed by long-term climate disruption. The stratospheric chemistry changes triggered by major impacts could persist long after surface temperatures recover. Sulfur compounds injected into the upper atmosphere form aerosol particles that reflect sunlight back to space, creating cooling effects that can last for years. The unusual chemical composition of 3I Atlas could produce atmospheric pollutants with even longer persistence times, potentially altering global climate patterns for decades. Threshold effects in Earth's climate system mean that atmospheric disruption could trigger irreversible changes that persist long after the immediate impact effects subside. The complex feedbacks between atmospheric composition, ocean circulation, ice sheet stability, and global temperature could amplify initial impact effects into permanent climate shifts. Even relatively modest atmospheric dust loading could push Earth's climate across tipping points that lead to ice age conditions lasting thousands of years. The vulnerability of modern technological civilization to atmospheric disruption extends beyond direct climate effects to include disruption of satellite communications, aviation, and electronic systems. The electromagnetic pulse generated by atmospheric impacts could disable electronic infrastructure across vast areas, while persistent atmospheric dust could interfere with solar power generation and disrupt GPS navigation systems that modern society depends upon for everything from agriculture to transportation. Perhaps most sobering is the realization that current climate models, developed to understand gradual environmental changes, may be inadequate for predicting the complex atmospheric dynamics triggered by major impacts. The sudden injection of vast quantities of energy and material into Earth's atmosphere represents a perturbation so far outside normal climate variability that existing models might fail to capture critical feedback mechanisms that determine whether civilization survives the aftermath. The sobering reality of our current detection and warning capabilities becomes starkly apparent when confronted with the prospect of tracking a fast-moving interstellar object like 3I Atlas that might suddenly change course or fragment into multiple threats. Despite decades of investment in asteroid and comet surveillance, our planetary defense infrastructure remains woefully inadequate for dealing with the unique challenges posed by objects originating from beyond our solar system, operating on timescales that compress months of warning time into weeks or even days. The Catalina Sky Survey, Linear, and NEOWISE programs that form the backbone of our near-Earth object detection network were designed primarily to catalog asteroids and comets following predictable elliptical orbits around the Sun. These systems excel at finding objects that return periodically, allowing multiple observation opportunities to refine orbital parameters and assess collision probabilities. 3I Atlas represents a fundamentally different challenge. A one-time visitor moving at velocities that dramatically compress observation windows and magnify the consequences of measurement uncertainties. Ground-based optical surveys face inherent limitations when tracking objects at 3I Atlas's extreme velocity. The apparent motion across the sky occurs so rapidly that standard astrometric techniques struggle to maintain positional accuracy over the extended periods required for precise orbit determination. Atmospheric turbulence, weather conditions, and the day-night cycle create gaps in observational coverage that become critical when dealing with objects whose trajectories can change significantly over timescales of hours or days due to outgassing or fragmentation events. The southern hemisphere bias of 3I Atlas's discovery trajectory compounds detection challenges for northern hemisphere observatories that comprise much of our global tracking network. While international cooperation has enabled coordinated observations, the geometric constraints of Earth-based astronomy mean that optimal viewing conditions exist for only a fraction of observatories at any given time. This coverage limitation becomes particularly problematic if the object undergoes sudden brightening due to fragmentation or increased outgassing activity. Space-based detection assets offer some advantages over ground-based systems but remain limited in number and observational capacity. The NEOWISE infrared survey telescope has provided crucial thermal observations of 3I Atlas, but its wide-field survey mode cannot provide the high-precision astrometry needed for detailed trajectory prediction. More capable space telescopes like Hubble and Webb require extensive scheduling coordination and can observe only single targets at a time, making them unsuitable for tracking multiple fragments if breakup occurs. The fundamental limitation lies in our detection threshold for small but dangerous objects. Current surveys reliably detect asteroids larger than about 1 kilometer in diameter at distances beyond Earth's orbit, but this threshold increases dramatically for faster-moving targets. 3I Atlas fragments smaller than several hundred meters might remain undetected until they approach within lunar distance, providing only days or hours of advance warning before potential atmospheric entry. Radar detection offers superior accuracy for orbit determination, but operates under even more restrictive range and sensitivity limitations. The most powerful planetary radar systems can track objects out to only a few astronomical units under optimal conditions, well inside 3I Atlas's current position. This technology becomes useful only during the final weeks of approach, when trajectory modification opportunities have essentially vanished, and emergency response preparations represent the only viable options. The computational challenges of processing observations from multiple telescopes and converting them into actionable trajectory predictions operate under time constraints that become increasingly severe as objects approach Earth. The orbital determination process requires days or weeks of observations to achieve the precision needed for reliable impact probability calculations for an object exhibiting non-gravitational accelerations due to outgassing. These computational timelines may exceed the advance warning period available for meaningful response. International coordination mechanisms that work adequately for predictable asteroid threats become strained when dealing with rapidly evolving situations involving interstellar objects. The Minor Planet Center and other coordinating bodies operate on timescales appropriate for objects discovered months or years before potential impact. 3I Atlas scenarios involving sudden trajectory changes or fragmentation events could unfold faster than existing coordination protocols can adapt to provide timely warnings to affected populations. Communication pathways between astronomical detection systems and emergency management agencies remain poorly developed for scenarios involving short warning times. While protocols exist for handling asteroid impact threats discovered years in advance, the infrastructure for rapid dissemination of warnings about imminent impacts from interstellar objects has never been tested under realistic conditions. The challenge becomes particularly acute for fragments that might threaten populated areas with only hours of advance notice. The false alarm problem presents another critical limitation for detection systems. Extreme velocities and unusual properties of interstellar objects increase the likelihood of misidentification or erroneous trajectory predictions that could trigger unnecessary emergency responses. Balancing the need for rapid warning against the costs of false alarms requires decision-making protocols that have never been validated for objects with 3I Atlas's characteristics. Perhaps most troubling is the complete absence of mitigation capabilities for fast-moving interstellar threats detected on short notice. Every proposed asteroid deflection technology, from kinetic impactors to nuclear explosives, requires years of advance warning to design, build, and deploy missions capable of altering object trajectories. Even the most optimistic scenarios for rapid response missions would require months of preparation time that simply may not be available for objects like 3I Atlas. The harsh reality is that our planetary defense capabilities, impressive as they may be for catalogued asteroids following predictable orbits, offer little protection against the unique threats posed by interstellar visitors whose behavior we cannot predict, and whose approach we may not detect until collision becomes unavoidable. The timeline for 3I Atlas's approach through our solar system operates with the relentless precision of celestial mechanics, each month bringing new risks as the object encounters different gravitational influences, thermal environments, and structural stresses that could transform a predictable passage into an unpredictable catastrophe. Understanding this temporal progression becomes crucial for identifying critical decision points where human response might still matter, and recognizing the narrowing windows during which any effective action remains possible. March through May 2024 represents the current observation phase, during which 3I Atlas remains at sufficient distance for detailed study, but close enough to reveal its unusual properties through increasingly powerful telescopic observations. During these months, the object's trajectory calculations become progressively more precise as additional astrometric data reduces positional uncertainties. However, this is also the period when signs of structural instability or unusual outgassing behavior might first become apparent, providing the earliest warnings of potential fragmentation or trajectory modification events. June marks the beginning of accelerated solar heating, as 3I Atlas crosses the orbit of Mars, entering the region where increased thermal stress begins to affect internal structure and outgassing rates. Historical data from solar system comets suggest this distance represents a critical threshold where previously stable objects can begin to exhibit signs of fragmentation or dramatic changes in gas production. For 3I Atlas, with its exotic composition and unknown internal architecture, this transition could trigger unpredictable behaviors that invalidate all previous trajectory calculations. July and August constitute the period of maximum uncertainty, as 3I Atlas approaches within 2 astronomical units of the Sun, entering the zone where solar heating becomes intense enough to drive vigorous outgassing and potentially catastrophic structural failure. During these months, non-gravitational forces from asymmetric gas ejection could alter the object's trajectory by thousands of kilometers, while thermal stress could trigger fragmentation events that transform a single threat into multiple unpredictable hazards scattered across the inner solar system. September represents the crisis month, with 3I Atlas reaching perihelion around the 28th and experiencing maximum thermal stress from solar radiation. This closest solar approach occurs at roughly 1 astronomical unit, placing the object well within the orbit of Earth and subjecting it to heating rates comparable to those experienced by sun-grazing comets, many of which disintegrate completely during such encounters. Any structural weaknesses developed during billions of years of interstellar wandering would likely manifest during this period of extreme thermal loading. October brings the critical post-perihelion phase when 3I Atlas begins its outbound journey, but remains close enough to the Sun for continued vigorous outgassing. This period presents the highest risk for Earth-directed debris if fragmentation occurred during the solar passage, as fragments ejected during perihelion heating could be redirected onto Earth-crossing trajectories by solar radiation pressure and ongoing outgassing forces. The object's approach to within roughly 2 astronomical units of Earth during this period creates the possibility for direct impact from large fragments. November and December mark the period when 3I Atlas passes closest to Earth's orbital region, reaching minimum distance of approximately 1.8 astronomical units in early December. While this remains a comfortable buffer under normal circumstances, fragments produced during earlier fragmentation could follow different trajectories that bring them much closer to our planet. This timeframe represents the last opportunity for detecting dangerous debris before potential atmospheric encounters occur. The first quarter of 2025 encompasses the extended risk period, when fragments following modified trajectories could continue to pose impact threats. Unlike the parent object's predictable hyperbolic escape, fragments could be scattered onto elliptical orbits that bring them back into the inner solar system repeatedly over periods of years or decades. During this phase, continued monitoring becomes essential for identifying delayed threats that might not become apparent until months after the original object's departure. Critical decision points occur throughout this timeline, with each phase offering progressively fewer options for meaningful response. The current observation phase represents the last opportunity for comprehensive characterization studies that might reveal structural weaknesses or behavioral patterns. The June transition period marks the final window for deploying rapid response space missions, though even optimistic scenarios would require months of preparation that may not be available. The July-August uncertainty period represents the point where human intervention becomes largely impossible, leaving emergency preparedness as the only viable response to potential threats. During this phase, trajectory modifications could occur faster than ground-based observations can track, while fragmentation events might create multiple simultaneous hazards that overwhelm detection and coordination capabilities. Perhaps most sobering is the realization that the most dangerous scenarios might unfold entirely within the September crisis month, leaving inadequate time for even basic emergency response measures. If 3I Atlas fragments during perihelion passage and ejects large debris toward Earth, the time between fragmentation and potential impact could be measured in weeks rather than months, compressing the entire disaster response timeline into periods shorter than required for effective evacuation or protection measures. The acceleration of risk as 3I Atlas approaches perihelion reflects fundamental physics rather than administrative convenience. Solar heating, gravitational perturbation, and structural stresses all intensify according to inverse square laws that concentrate the most dangerous possibilities within the shortest time periods, creating a temporal bottleneck where decades of gradual approach culminate in weeks of maximum hazard that could determine the fate of human civilization. The harsh reality confronting humanity's planetary defense capabilities becomes starkly apparent when measured against the unique challenges posed by 3I Atlas and other fast-moving interstellar objects. Every proposed asteroid deflection technology currently under development assumes years or decades of advance warning, leisurely mission planning timelines, and target objects following predictable orbits that allow multiple intercept opportunities. 3I Atlas shatters every one of these comfortable assumptions, revealing our planetary defense infrastructure as fundamentally inadequate for dealing with threats that operate on cosmic rather than human timescales. NASA's Double Asteroid Redirection Test, successfully demonstrated in 2022 against the asteroid Dimorphos, represents the current state-of-the-art in kinetic impact deflection technology. This mission required nearly 4 years from conception to impact, involving careful trajectory planning, spacecraft design, launch operations, and cruise phase navigation to reach a target asteroid following a well-characterized orbit. The entire mission architecture assumes stable, predictable target behavior and sufficient time for course corrections during the multi-year flight to the asteroid system. Applying these timescales to 3I Atlas reveals the impossibility of mounting any kinetic deflection mission. Even if a deflection spacecraft had been launched immediately upon the object's discovery in January 2024, it would arrive at the target location months after 3I Atlas had already passed through the inner solar system and departed toward interstellar space. The object's extreme velocity means that intercept trajectories require energy expenditures far exceeding the capabilities of current launch vehicles, while its hyperbolic escape orbit provides no opportunity for the gravitational assists that make most deep space missions feasible. Nuclear deflection options, long considered the ultimate planetary defense technology for the most dangerous asteroids, face even more severe constraints when applied to interstellar objects. The proposed nuclear explosive devices designed for asteroid deflection assume careful placement on or near the target object's surface, requiring rendezvous missions that can match velocities and maintain station keeping for extended periods. 3I Atlas's 32 km/s velocity makes such rendezvous impossible with any conceivable propulsion technology, while its unknown structural properties complicate predictions about how nuclear explosions might affect its trajectory. Solar sail and laser deflection concepts that rely on gradual momentum transfer over extended time periods become completely useless against objects like 3I Atlas. These approaches require continuous application of force over years or decades to produce meaningful trajectory changes, timeframes that exceed the entire duration of the object's solar system passage. The inverse relationship between deflection effectiveness and target velocity means that the most dangerous fast-moving objects are precisely those least susceptible to gentle deflection techniques. Even theoretical proposals for rapid response deflection systems face insurmountable technical challenges when confronted with 3I Atlas scenarios. Concepts for space-based interceptor networks assume target detection and characterization periods measured in months, allowing time for trajectory optimization and mission planning. The compressed timelines associated with interstellar objects compress these planning periods into weeks or days, intervals too short for any meaningful mission design process. The fragmentation scenario presents additional complications that render conventional deflection approaches not just inadequate but potentially counterproductive. If 3I Atlas breaks apart during its solar passage, creating multiple fragments on diverse trajectories, any deflection effort would need to address dozens or hundreds of individual threats simultaneously. Current deflection technologies can engage only single targets, making them useless against distributed threat scenarios that multiply faster than deflection missions can be planned and executed. International coordination mechanisms that govern asteroid deflection missions operate under peacetime bureaucratic timelines completely inappropriate for rapidly evolving interstellar threats. The United Nations Committee on the Peaceful Uses of Outer Space, responsible for coordinating international responses to asteroid threats, requires months or years to develop consensus positions on deflection missions. 3I Atlas scenarios demand decision-making and implementation timescales measured in weeks, compressing years of normal diplomatic and technical coordination into periods shorter than most government budgeting cycles. The technological gaps become even more apparent when considering the unique challenges posed by 3I Atlas's exotic composition and structure. Deflection mission planning requires detailed knowledge of target mass, density, rotation state, and structural integrity to predict how applied forces will affect trajectory. The fundamental uncertainties surrounding 3I Atlas's physical properties make it impossible to design effective deflection strategies even if adequate time and resources were available. The ground-based laser systems proposed for deflecting smaller asteroids through surface ablation face insuperable power and targeting requirements when applied to objects like 3I Atlas. The extreme range and high angular velocity of the target would require laser systems with power outputs comparable to national electrical grids, maintained with tracking precision that exceeds current technological capabilities by orders of magnitude. Perhaps most sobering is the realization that emergency evacuation and civil defense measures represent the only meaningful responses available for 3I Atlas-class threats. Unlike asteroid deflection missions that can eliminate threats entirely, evacuation efforts merely relocate potential casualties while accepting that impacts will occur. The scale of evacuation required for major impact scenarios involving city-sized fragments exceeds the logistical capabilities of most national governments, particularly when warning times might be measured in days rather than months. The political dimensions of planetary defense readiness reveal additional inadequacies in current institutional arrangements. No existing governmental or international body possesses the authority, resources, and technical expertise necessary to coordinate rapid responses to interstellar threats. Space agencies focus on scientific missions and lack military operational capabilities, while defense establishments lack space expertise and operate under peacetime acquisition timelines incompatible with cosmic emergencies. The stark conclusion emerging from this assessment is that humanity remains essentially defenseless against the category of threats represented by 3I Atlas, possessing neither the technological capabilities nor the institutional frameworks necessary to mount effective responses to fast-moving interstellar objects detected on timescales shorter than our planning and development cycles can accommodate. The mathematics suggest 3-eyed Atlas will pass harmlessly through our solar system, another cosmic curiosity catalogued and forgotten. But mathematics assume perfect knowledge of initial conditions, complete understanding of physical processes, and the absence of unknown factors. When dealing with an object that embodies billions of years of cosmic history we've never studied, that carries chemical signatures from stellar environments we've never encountered, that represents a class of phenomena we've only just begun to recognize. Such assumptions become articles of faith, rather than scientific certainty. The trajectory calculations that provide our comfort depend on models calibrated against solar system objects with known formation histories and predictable behaviors. 3I Atlas operates outside these comfortable boundaries, shaped by gravitational encounters we cannot reconstruct, modified by radiation exposure we cannot quantify, and governed by internal processes we cannot observe. The confidence intervals surrounding its predicted path reflect measurement precision rather than fundamental understanding of what determines its actual motion through space. Perhaps most troubling is our complete inability to respond meaningfully if those predictions prove inadequate. Our planetary defense capabilities, impressive as they appear when measured against slowly approaching asteroids detected years in advance, offer no protection against objects that compress warning times into periods shorter than our institutional response capabilities can accommodate. The real question isn't whether 3I Atlas will end our world. It's whether we're prepared to live in a universe where such questions can never be answered with absolute certainty, where ancient wanderers from the space between stars will continue to arrive unannounced, carrying with them the humbling reminder that our cosmic neighborhood remains fundamentally mysterious and potentially dangerous in ways we're only beginning to comprehend.